Usually, making a computer faster just means brute force, like a bigger engine.
Right, exactly.
You want the car to go faster, you drop in a V8 with more horsepower, and the mechanic basically just points at it and says, there it is, more power.
Yeah, that's a classic approach.
And we do the exact same thing with hardware. We throw more gigahertz at the problem, we pack more transistors onto the silicon die, we widen the bus.
Pure, unadulterated speed.
Right. And it's clean, it makes sense, and honestly it is comforting because you can point to the processor and know exactly why, say, your spreadsheet loaded faster.
Yeah, you can actually see the spec sheet difference.
Exactly. But today, we are looking at a piece of software that makes computers up to, and this is a real number, 192 times faster simply by telling the processor cores to, well, stop checking up on each other.
Yeah, the transition from single-core performance to parallel processing, it completely shatters that bigger engine analogy.
How so?
Well, we are no longer dealing with a single, incredibly fast mechanic. We're dealing with an entire factory floor of mechanics.
Oh, I see.
And the moment you introduce multiple workers, the primary bottleneck is no longer how fast they can, turn a wrench.
Right.
The bottleneck becomes coordination. It becomes management.
Like who's doing what?
Exactly. How do you assign the work? How do you make sure two mechanics aren't trying to modify the exact same part of the engine at the exact same time?
Chaos, basically.
Total chaos. We are looking at a computational landscape today that is really an exercise in microscopic coordination.
Okay, let's unpack this. Our source material today is the technical documentation for a brand new Rust-based static execution engine. It's called gnosis-frf.
Which stands for fork, race, fold.
Right, fork, race, fold. And for you listening, we're taking a deep dive into this because this documentation doesn't just present a new software tool. It really presents a philosophical argument against the current industry standard.
A massive philosophical shift, honestly.
Yeah, because for anyone programming in Rust who wants to run operations in parallel, the current heavyweight champion is a library called Rayon.
Rayon is ubiquitous.
It is. And Rayon relies on a dynamic approach called work stealing. It's famous for being incredibly flexible, but gnosis-frf points out that this flexibility introduces a microscopic computational tax on every single operation.
A tiny tax, but it adds up.
Exactly.
Yeah.
So gnosis-frf asks this deeply provocative question. What if you have perfectly uniform data and you just want to completely abolish that tax?
To really appreciate the magnitude of what gnosis-frf is doing here, we have to look closely at the mechanics of Rayon's work-stealing DEX.
DEX.
Yeah, the word DEC is short for double-ended queue.
Okay, got it.
In a dynamic work-stealing system like Rayon, the operating system spins up multiple worker threads, and each of those threads is given its own queue of tasks to complete.
So everyone gets a to-do list.
Exactly. If you have a massive data set, it gets distributed among these DECs. The brilliance of Rayon, though, is in how it handles imbalance.
When someone finishes early.
Right. When a thread finishes everything in its own queue, it does not sit idle. It actively surveys the queues of the other threads. Yeah, if it sees that another thread is completely bogged down with a heavy workload, the idle thread will literally steal work from the bottom of that struggling thread's queue.
That sounds incredibly efficient on its face. I mean, you are guaranteeing that no single processor core is sitting there doing nothing while another core is drowning in work.
You're maximizing hardware utilization.
Exactly. No wasted time.
And for unpredictable, unbalanced workloads, it is a masterclass in scheduling.
Right.
Consider a program designed to process a batch of thousands of images. One image might be a tiny, simple 16 by 16 pixel icon. That takes a fraction of a millisecond to process.
Super fast.
The very next image in the queue might be a massive 4K panoramic photograph requiring complex color grading and compression.
So that's going to take way longer.
Way longer.
All right.
The thread that draws the icon will finish almost instantly. Under a rigid system, that thread would just wait.
Just sit there twiddling its thumbs.
Right. But under Rayon's work-stealing system, that thread immediately pivots, looks at the thread processing the panorama, and steals a chunk of the underlying pixels to help finish the job.
That's amazing.
It is. But that dynamic flexibility is fundamentally not free.
Right, because every time a thread looks at its own queue to pop a task, or looks at someone else's queue to steal a task, or, moves data around to balance the load, it takes a tiny bit of computational effort,
It's an administrative overhead.
a management tax.
Exactly. The mechanism of stealing requires specialized atomic operations. You have to ensure that two threads don't accidentally grab the exact same task from the queue at the exact same nanosecond.
Right, because that would be a disaster.
Total disaster. If thread A and thread B both try to steal the last remaining image from thread C's queue simultaneously, the system could corrupt the memory or process the image twice.
But how does Rayon prevent that?
To prevent this, Rayon uses microscopic locks and atomic compare and swap instructions. The CPU has to briefly pause, check the state of the memory, lock it, take the task, and then unlock it.
That sounds heavy.
Well, when you are traversing perfectly uniform data, meaning every single task takes the exact same amount of time to complete, this dynamic stealing mechanism is completely unnecessary overhead.
Because nobody needs to steal anything.
Exactly. The threads are all going to finish their initial queues at the exact same time anyway, so why are we paying the computational tax of constantly checking in on each other?
Okay, I see. So if you are calculating dense mathematical tensor shards, or running cellular automata, or processing swarm agent loops, the data is perfectly even.
Yes.
There are no panoramas and no icons. There are just identical blocks of math.
Perfectly predictable.
I was thinking about this, and it reminds me of a massive restaurant buffet.
Okay, I like this.
Think about a giant dining room with 100 tables. Rayon is like having a team of dynamic servers constantly running around the room, looking over everyone's shoulders to see if any tables have unfinished plates they can help clear.
Right, that is work stealing.
And it is absolutely great for unpredictable crowds where some people eat fast and others linger. But think about the wasted energy if everyone in the entire restaurant eats at exactly the same speed.
Yes, the servers are just running in circles.
Burning calories, checking on people who don't need help at all.
You are burning energy on the mechanism of coordination rather than the work itself.
Right.
The CPU cycles spent managing the queues and executing atomic locks are cycles not spent crunching the actual data.
So gnosis-frf takes a completely different approach. It is like a kitchen that perfectly portions out exactly equal meals to every single table in advance, bypassing the servers entirely.
They call this static partitioning.
Right. And the model is named fork, race, fold. Let's break down the physical reality of what those three words mean in this architecture, starting with fork.
The fork phase is about how the threads are managed before the work even begins.
Okay.
Instead of dynamically allocating new operating system threads every time a parallel loop is called, gnosis-frf utilizes a set number of background static threads.
The documentation calls this variable K, right?
Exactly, K threads. These threads are created once when the program starts, and when there is no work, they don't terminate, they just go to sleep.
They just hang out.
They wait at what the documentation calls a persistent, lock-free convar barrier.
Now, creating a new thread is a notoriously heavy operation for an operating system, right?
Oh, very heavy.
The OS has to allocate a new stack in memory, set up thread local storage, and, register the thread with the kernel scheduler.
Today's time.
So by keeping them persistent, you are entirely bypassing the OS kernel during the actual execution loop. They're already alive, just parked at a starting line, waiting for the gun to go off.
And the race phase is the gun going off.
Oh, okay.
The memory block that needs to be processed is statically divided into K perfectly sized lanes.
So if your CPU has 8 cores,
And the system has spun up 8 static threads, the data array is sliced into exactly 8 absolutely equal chunks.
no queues.
There are no dynamic queues. There is no stealing mechanism. Every thread gets a pointer to its specific lane in memory, and the race begins.
Just a straight sprint.
Because the underlying assumption is that the data is uniform, the architecture relies on the mathematical certainty that all 8 threads will run the race at the exact same speed.
And finally, we have the fold phase. Once the threads race down their respective lanes and finish their chunk of the calculations, they have to bring the results back together, right?
Right, they collapse the individual results into a single answer.
And the documentation specifically notes that they do this using atomic-free, SIMD-friendly vectorization loops.
Yeah, SIMD stands for single instruction, multiple data.
I've heard of that. What is it practically?
It is a feature built directly into modern processors like the AVX instructions on Intel or Neon on Apple Silicon.
Oh, sure.
It allows a single CPU core to perform the exact same mathematical operation on multiple pieces of data in a single clock cycle.
Wait, really? How many?
Well, instead of adding 2 numbers together, A SIMD instruction can add, say, 8 pairs of numbers together simultaneously.
That's a huge speed up.
It is. However, compilers can only automatically utilize these SIMD instructions if they can prove that the memory being accessed won't be modified by something else unexpectedly.
Ah, right. If things are moving around, the compiler gets scared.
Exactly. Because gnosis-frf guarantees that each thread owns its static lane entirely and there are no atomic locks or dynamic queues interfering, the compiler can optimize the fold phase to use these SIMD hardware instructions to their absolute maximum potential.
That's brilliant.
Once the fold is complete, the threads resynchronize at the execution barrier, ready for the next task.
So we have this beautiful theory of static partitioning versus dynamic work stealing. But I want to look at the actual raw performance numbers.
The benchmarks.
Yeah, the benchmarks run on Apple Silicon hardware are where the reality of this architectural difference becomes just staggering. We need to look at the dispatch overhead.
Right, the setup costs.
This is just the administrative cost of handing out the work before the computation even begins. The source states that Rayon takes about 5 microseconds to inject a task into a deck and manage the associated locks. What is the dispatch overhead for gnosis-frf?
It's approximately 200 nanoseconds per call.
Wait, let's contextualize that scale for a second.
And a big jump.
A microsecond is a millionth of a second. A nanosecond is a billionth of a second.
Yes.
So Rayon takes 5,000 nanoseconds to dispatch the work, and FRF takes 200 nanoseconds.
Yes.
That is a 25 times reduction in just the administrative overhead of saying, here's your job, go do it.
To truly ground those numbers, you have to look at what physical hardware does in a nanosecond.
Okay, let's do it.
Modern processors operate in the multi-gigahertz range. A 3 gigahertz processor executes 3 billion clock cycles per second.
Which means
That means a single clock cycle, the fundamental heartbeat of the processor executing an instruction, takes about a third of a nanosecond.
wow.
Rayon's 5,000 nanosecond dispatch overhead equates to roughly 15,000 wasted clock cycles per core.
15,000.
That is 15,000 instructions where the CPU is just doing paperwork, moving pointers around, and checking locks.
And FRF?
FRF cuts that paperwork down to about 600 clock cycles.
That is insane. And we can see exactly how that translates into the benchmark results for uniform workloads. Let's look at an incredibly small, fast workload of just 100 uniform items.
The smallest test.
The median time for Rayon to complete it was 642.1 microseconds. The median time for gnosis-frf was 3.52 microseconds.
At 182.4x improvement.
182 times faster.
It fundamentally reclassifies what is possible. It moves parallel processing from something you only invoke for massive, heavy computations to something you can invoke for incredibly short, rapid bursts of math.
I do want to point out the behavior of the data as the workload scales up, though. As we give the system more work, that massive 182 times gap starts to narrow.
It does.
At 1,000 items, FRF is 20.7 times faster. And at 10,000 items, it is 6.6 times faster. Why does the relative advantage shrink as the volume of work increases?
This demonstrates the principle of amortized cost.
Okay, break that down for me.
Consider the 5 microsecond tax that Rayon charges for dispatching work. If the actual mathematical computation you are trying to perform only takes 1 microsecond in total, then a 5 microsecond tax is utterly devastating.
Oh, absolutely. The overhead is 5 times larger than the job itself.
You are spending 500% more time organizing the work than doing the work.
Right.
That is exactly what happens at the 100-item level. The actual computation is so minuscule that Rayon's dispatch time dominates the entire measurement.
But as the job gets bigger, the 5 microsecond tax stays exactly the same, but it becomes a much smaller percentage of the total runtime.
Precisely. When you scale up to processing 10,000 items, the raw computation might take 500 microseconds.
Okay.
At that point, Rayon's 5 microsecond administrative tax is still there, but 5 microseconds added to 500 microseconds is barely a 1% penalty.
So it fades into the background.
Exactly. The sheer volume of real heavy computation dilutes the fixed cost of Rayon's deck pushing and popping.
Though, FRF's 6.6x speed up at that 10,000 item scale is still phenomenal.
Oh, definitely. It's driven by the SIMD vectorization and cache alignment we will discuss shortly, but the fixed cost dispatch advantage naturally amortizes away.
So where does someone actually use a system that is optimized for tiny microsecond scale uniform workloads?
There are a few specific fields.
The documentation explicitly calls out domains like high-frequency trading tick handlers, game loop frame updates, real-time rendering, and streaming data pipelines. Basically anything that needs to run perfectly over and over incredibly fast.
Yes.
They say any program calling parallel iteration more than once a second lands in FRF's sweet spot. But look at high-frequency trading, or HFT, because the stakes there are incredibly tangible.
In high-frequency trading, algorithms are reacting to market data ticks and executing buy or sell orders.
And time is money. Literal money.
Unbelievable amounts of money. We are talking about infrastructure where financial firms spend hundreds of millions of dollars to lay physically straighter fiber optic cables between data centers in Chicago and New York.
Just to shave off a single millisecond of light travel time, right?
Yes. They use specialized FPGA hardware on their network cards to parse data before it even reaches the main CPU.
That is wild.
In that environment, a 5-microsecond delay in your software's parallel execution engine means your competitor's algorithm evaluates the market tick and executes the trade before yours does.
You lose the trade.
You lose the trade and you lose the money. They require the absolute floor of physical latency, and critically, they require it to be deterministic.
Deterministic, meaning the execution happens exactly the same way in the exact same amount of time every single time the loop runs.
Precisely.
In a game loop architecture, determinism is just as vital, right?
Oh, absolutely. To achieve a smooth 60 frames per second, the game engine has exactly 16.6 milliseconds to calculate physics, update AI behaviors, process player input, and render the entire scene.
That's a tight window.
If the execution engine randomly decides to pause for 2 milliseconds to reorganize a dynamic work-stealing queue, or wait for an atomic lock to clear, the engine misses the 16.6 millisecond deadline.
And what happens?
The frame drops. The player experiences visual stutter.
Ah, nobody likes that.
Nobody. Gnosis-frf's static partitioning provides a mathematical guarantee of execution time because the path is set before the race begins.
So it is one thing to draw a diagram with equal lanes. It is another thing entirely to make the physical silicon of the processor respect those lanes without tripping over itself.
That's the real trick.
Right. How does gnosis-frf pull this off at the hardware level? The documentation highlights 0 runtime decallocations, which we've covered. But the next architectural pillar is cache line alignment.
This is a beautiful piece of engineering.
The text states, and I'll quote here, "The engine computes the greatest common divisor of the memory size of the data type, and 64 bytes to guarantee that static thread division never slices across a CPU cache line, definitively neutralizing false sharing."
That's a very dense sentence.
It is. Let's translate this into the physical world. What exactly is a CPU cache line, and what is false sharing?
This requires a brief dive into memory hierarchy. We often think of RAM main memory as fast.
Yeah, more RAM means a faster computer, right?
Well, relative to the speed of a modern CPU core, RAM is agonizingly slow. It can take over 100 nanoseconds for a processor to reach out to RAM, find a piece of data, and bring it back.
And when we're talking about nanoseconds,
That's an eternity. To prevent the CPU from constantly stalling while waiting for RAM, processors have built-in ultra-fast memory called L1, L2, and L3 cache.
like little pockets of memory right next to the processor.
Exactly. L1 cache is located directly on the processor core itself and can be accessed in about a single nanosecond.
Okay, so the CPU wants to keep everything it is actively working on inside that L1 cache. But it doesn't just pull over 1 byte at a time from the slow RAM, right?
No, it pulls data in chunks. The hardware designers assume that if your program needs a specific byte of data right now, it will probably need the neighboring bytes of data in the next few nanoseconds.
Makes sense, like grabbing a whole textbook instead of just one page.
Right. This is called spatial locality. So when the CPU requests a single variable from RAM, the memory controller grabs a contiguous 64-byte block of memory surrounding that variable and pulls the entire block into the L1 cache.
And that 64-byte chunk is called a cache line.
That's the cache line.
I have an analogy for this. Tell me if this works. Imagine 2 office workers forced to write on the exact same piece of physical paper on a shared desk, constantly bumping elbows.
Okay, tracking.
Worker A is thread 1 running on core 1. Worker B is thread 2 running on core 2. They're working on completely different tasks. Worker A is writing on the top half of the paper, modifying data A.
Worker B is on the bottom half.
Modifying data B. They don't care about each other's work at all.
The problem arises when data A and data B reside within the exact same 64-byte block of memory in RAM. Core 1 pulls the cache line containing data A into its private L1 cache. Core 2 simultaneously pulls the identical cache line containing data B into its private L1 cache.
Right.
Now, thread 1 modifies data A.
Ah, because core 1 just changed the data, the version of the cache line sitting over in core 2 is suddenly out of date.
It is stale.
Even though core 2 only cares about data B, the physical 64-byte block they are both sharing has been altered. Every time worker A erases something, they shake the whole desk, and worker B messes up their handwriting.
That's a great way to put it. And the hardware cache coherency protocol has to intervene.
What does that mean?
It forces Core 2 to throw away its entire L1 cache line, stall its execution, go all the way back out to main memory or the shared L3 cache, and fetch the newly updated 64 bytes.
Just because the other guy updated his half.
Yes. And if thread 2 is simultaneously modifying data B, the exact same thing happens in reverse. Core 1's cache is invalidated.
It's a nightmare.
The two cores end up in a vicious ping-pong match, constantly invalidating each other's caches and forcing slow trips to main memory over and over again.
And this is false sharing.
This phenomenon is exactly what false sharing is. The software threads aren't actually sharing variables, but because the variables happen to share the same physical 64-byte block of hardware memory, they utterly destroy each other's performance.
But gnosis-frf mathematically ensures every worker gets their own perfectly separated desk, so the CPU never gets confused.
Exactly.
The engine calculates the alignment before the race even starts. By taking the data type, size, and memory and finding the greatest common divisor with 64 bytes, it can calculate exactly where the 64-byte boundaries fall.
It's a brilliant preemptive strike.
It guarantees that when it slices the memory into k-static lanes, the partition line never, ever cuts through the middle of a 64-byte cache lane.
It is an elegant application of basic number theory to solve a really severe hardware bottleneck.
I love when high-level math solves physical engineering problems.
By aligning the data partition perfectly with the physical architecture of the cache, false sharing is entirely neutralized. Core 1 and Core 2 operate on independent cache lines that never overlap.
So the hardware cache coherency protocol stays silent.
And the cores run at maximum speed.
That level of microscopic precision extends to the actual dispatch mechanism too, doesn't it? The documentation notes that it uses lock-free dispatch.
Right.
It mentions plain writes to the shared job slot, a release door to a generation atomic, and an unsafe cell for the job data.
That's a mouthful.
Well, for developers working in Rust, seeing the word unsafe usually triggers alarm bells, doesn't it?
Oh, massive alarm bells.
Rust is famous for its borrow checker, which strictly prevents data races by enforcing rules about how memory can be accessed. Using an unsafe cell sounds incredibly dangerous.
In the Rust programming language, memory safety is the foundational design principle. The compiler enforces a strict rule. You can have multiple immutable references to a piece of data, meaning many threads can read it, or you can have exactly one mutable reference, meaning only one thread can change it.
But you can't do both.
You can never have both simultaneously. This entirely prevents data races at compile time.
So what is the unsafe cell doing?
An unsafe cell is a deliberate escape hatch provided by the language. It allows you to mutate data even when there are multiple references to it.
Wait, really?
Yes, essentially telling the compiler, turn off the safety checks. I know this looks like a data race, but I have built my own complex mathematical and logical guarantees that this memory access is actually safe.
And the mechanism they use to provide that guarantee is the release store to a generation atomic.
Exactly.
Now, an atomic operation is a hardware-level instruction that is guaranteed to be indivisible, right? It cannot be interrupted halfway through.
That's right. An atomic variable acts as the single source of truth between the threads. Here is how the lock-free dispatch unfolds without violating memory safety.
Walk me through it.
The main thread has the raw job data, the pointers to the memory that needs processing. It takes that data and writes it directly into the unsafe cell.
Right.
At this moment, the worker threads are not looking at the unsafe cell. They are only watching the generation atomic, which acts like a flag.
Once the main thread finishes writing the data into the cell, it flips the atomic flag.
Right. The specific terminology, a release store, dictates the memory ordering.
On memory ordering.
Modern CPUs aggressively reorder instructions to run faster. A release store acts as a one-way memory fence.
Like a physical barrier.
Mathematically, yes. It guarantees to the hardware that every single memory write that happened before the flag was flipped, specifically the writing of the job data into the unsafe cell, must be fully visible to all other cores before they see the flag change.
Okay, I follow. And the worker threads.
The worker threads are executing an acquire load on that atomic flag. The moment they see the flag flip, the memory ordering guarantees that the data inside the unsafe cell is fully settled and safe to read.
So there are no heavy software mutexes, no operating system locks, just a single microscopic integer being flipped in memory, synchronized at the hardware level.
This is exactly why the dispatch overhead is 200 nanoseconds.
But it raises a critical question about the workable threads. What are they actually doing while they wait for that flag to flip?
Ah, the wait state.
Yeah, the documentation details a hybrid worker wait, short spin, before park, so tight loops never pay the park and park round trip.
This touches on how operating systems manage power and resources. If a thread hits a barrier and has nothing to do, the OS kernel normally intervenes and parks the thread.
Reading.
It saves the thread's execution state, flushes its registers, and puts it to sleep so the CPU core can be used by another program, maybe your web browser or background music player.
But parking and unparking a thread requires a context switch.
And a context switch is computationally expensive. Waking a parked thread back up can easily take tens of microseconds.
Right. If the program is trying to run a game loop every 16 milliseconds, or an HFT algorithm where 5 microseconds is a lifetime, you cannot afford to wait tens of microseconds just to wake your threads up.
It would completely obliterate the 200 nanosecond dispatch time we just praised.
Exactly.
To circumvent the OS kernel, the worker threads utilize a spin wait. Instead of going to sleep, the thread enters a tiny, incredibly tight while loop.
So it's awake, but just circling.
Yes. It continually checks the atomic flag, asking the CPU, is it flipped yet? Is it flipped yet? Is it flipped yet? Over and over again.
For how long?
It does this for roughly 20 microseconds. If a new job is dispatched by the main program during that 20 microsecond window, which is highly likely in a paid game loop or a streaming data pipeline, the worker thread is already awake.
Running on the CPU core.
And instantly sees the flag flip. It grabs the work with zero unpark latency.
But spinning indefinitely would be a disaster.
Oh, complete.
The thread is technically running at 100% CPU utilization, just checking a flag. It generates heat and drains battery power while doing no actual work.
Which is why it is a hybrid wait. If 20 microseconds elapse and the flag hasn't flipped, the thread assumes the workload is sporadic and finally yields to the operating system, allowing itself to be parked.
The genius, though, is that the spin duration isn't rigidly fixed at 20 microseconds.
It learns.
The engine is self-regulating. It uses an atomic U32 that tunes the spin budget using an README.md style additive increase, multiplicative decrease, based on a metacognitive chain called Taylor's C0, C1, C2.
Yes.
This sounds like an engine that dynamically adjusts its own idle speed based on how traffic is flowing.
The scheduling logic is observing its own historical performance to predict the future. C0 represents the unknown cadence between dispatches, the actual timing of the workload.
Okay, so that's reality.
C1 is the observation phase.
Yeah.
The engine tracks how often a thread ends up parking versus how often it successfully catches a job while spinning.
And C2.
C2 is the adjustment mechanism. If the engine notices a pattern where the thread parks, goes to sleep, and is immediately woken up a microsecond later, it realizes its spin budget is too short.
Right. It shouldn't have gone to sleep.
Exactly. It additively increases the spin budget, extending it slightly to try and catch the next dispatch without parking.
What if it spins for way too long?
If the dispatches are coming far apart and the thread is spinning for a long time before eventually parking anyway, it multiplicatively decreases the budget, rapidly shrinking it to save power.
It behaves very similarly to how TCP congestion control algorithms manage data packets across the internet.
Yes, it probes the environment and adapts its parameters.
Before we move on to what happens when data isn't perfectly uniform, we need to address the real-world engineering fallbacks built into gnosis-frf.
The DOSM fallback.
Yeah, it says it gracefully downgrades to sequential deterministic loops for WASM. WebAssembly, or WASM, allows you to run high-performance compiled code like Rust directly inside a web browser. Why does a web browser require a fallback that kills the parallel execution entirely?
Security sandboxing.
Yeah.
To achieve true parallel shared memory processing in a browser environment, WebAssembly relies on a feature called shared area buffer.
Okay.
It allows multiple web workers to access the exact same block of memory simultaneously. However, several years ago, the computing industry was rocked by hardware vulnerabilities known as Spectre and Meltdown.
Oh, I remember those.
These flaws allowed malicious code to read protected memory by exploiting the timing of how the CPU speculatively executed instructions.
And how does that relate to WASM?
Because shared array buffer provides highly precise shared timing mechanisms, it could be weaponized to read sensitive data like passwords or session tokens from other tabs in the browser.
Oh, wow.
Consequently, many browser vendors heavily restricted or entirely disabled shared array buffers unless strict cross-origin isolation headers are present.
So if the environment doesn't allow shared memory, the persistent pool of K threads simply cannot function.
You're blind.
The locks, the atomics, the shared lanes, it all relies on them looking at the same physical memory space.
Right. And rather than crashing or throwing an unrecoverable error, gnosis-frf queries the environment at runtime.
Smart.
If it detects that shared array buffer is unavailable, it gracefully degrades. It abandons the persistent thread pool and executes the workload as a standard single-threaded sequential loop.
It loses the parallel speedup, but it maintains determinism and correctness, which ensures the application continues to function for the end user.
Exactly.
I deeply appreciate the honest caveat section of the documentation.
Me too.
It builds immense trust when engineers transparently lay out the exact scenarios where their tool falls apart. The primary caveat they highlight is tail variance.
Yep.
The text reads, and I quote, "Lock-free dispatch means fastest case latency is lightning. But if the pool cools, meaning greater than 100 meters between calls and workers park, the next dispatch pays an on-park cost. Individual slow samples can be 100x to 1000x the median on sustained load benches."
This is the inescapable consequence of bypassing dynamic queues.
Why is that?
If your application experiences a lull, perhaps it is waiting for a large network packet to download or waiting for a user to click a button, the worker threads quickly exhaust their spin budget and go to sleep.
Like we just talked about.
Exactly. When the burst of data finally arrives and the execution loop is called, the main thread has to ask the operating system to wake up all K worker threads. The dispatch time spikes from 200 nanoseconds to potentially hundreds of microseconds.
So the first execution after pause is painfully slow. But once the threads are awake, the subsequent executions immediately drop back down to lightning speed.
Yes. And RAN's dynamic work stealing architecture can actually absorb sporadic, unpredictable traffic patterns more gracefully because it doesn't rely on the threads being rigidly synchronized at a starting line.
Ah, I see.
gnosis-frf requires the threads to be hot and ready. The self-regulating spin mitigates this, but the physics of OS kernel parking are absolute.
They also warn that benchmark noise is extreme at sub-millisecond scales. They cite the macOS scheduler, 4P plus 4E core routing, and thermal state as dominating the measurement floor.
At the single-digit microsecond level, you are no longer just measuring the efficiency of your code, you are measuring the ambient environment of the silicon.
The physical temperature of the chip.
Exactly. Modern processors, particularly Apple Silicon, use heterogeneous computing. They have performance cores, the P cores, that run at high clock speeds and consume a lot of power.
And efficiency cores, the E cores that run slower but save battery.
Right. The operating system scheduler is constantly analyzing the system load and dynamically moving threads between the P and E cores.
So if the OS decides to move one of gnosis-frf's K threads to an efficiency core right before the race begins.
That thread will run significantly slower than its peers, ruining the uniform execution time.
Wow.
Furthermore, if the CPU temperature spikes, the hardware will thermal throttle, slightly reducing the clock speed to prevent damage. When your entire execution takes 3 microseconds, a 10% thermal throttle completely skews the benchmark data.
So we have spent the first half of this deep dive exploring the beauty of perfect, uniform data. Static partitioning, mathematically aligned cache lines, lock-free dispatch.
It's elegant.
It is breathtakingly elegant in a vacuum. But the real world is messy. Data is rarely perfect. So how does a rigidly static system handle chaos? What happens when one of those K-way lanes suddenly has a massive pothole in it?
This represents the fundamental vulnerability of any purely static K-way split. The documentation is explicit here. The static partition fails catastrophically when one chunk of data takes significantly longer to process than its peers.
Let me set up a scenario.
Go for it.
Imagine you are rendering a 3D scene in a video game. You divide the screen into 8 equal geometric squares, assigning 1 square to each of your 8 static threads. 7 of those squares happen to be pointing at the empty blue sky.
Easy work.
Right. The math required to render a flat blue pixel is trivial. Those 7 threads scream down their memory lanes and finish their work in a single microsecond. But the 8th square contains a massively complex character model with reflective armor, translucent materials, and a dense particle system for magical effects.
The nightmare square.
Exactly. The 7 threads that finished instantly arrive at the execution barrier and park. They cannot return to the main program, and they cannot start the next frame because they must wait for the slowest thread to finish before the fold phase can occur.
Because it's a barrier.
Right. The thread rendering the complex character might take 10 milliseconds to finish. For those 10 milliseconds, 7 out of your 8 CPU cores are sitting completely idle, doing zero work.
The parallel efficiency of the system collapses.
Completely.
You have lost all the benefits of multi-core processing because you statically bound the work to the threads before knowing how heavy the work actually was.
To solve this without reverting to Rayon's dynamic work stealing, gnosis-frf introduces a mechanism called with subchunks and an auto-tuning variant called with subchunks auto.
This is where things get really clever.
The premise is that it splits n elements into m coarse-grained chunks, where m is significantly greater than k, the number of threads.
Right, so instead of splitting the 3D scene into 8 giant squares for the 8 threads, the system partitions the scene into, say, 64 much smaller squares.
Okay.
The number of threads, k, remains 8, but now they are not assigned a single permanent lane. They draw their work from a central repository.
Wait, I have to push back here.
Let's hear it.
Didn't we just spend 20 minutes establishing that gnosis-frf's core identity is avoiding the administrative tax of dynamic queues? If the threads are drawing work dynamically from a central repository, isn't that just a queue? Doesn't this sub-chunking violate the entire premise of the static architecture?
It is a vital distinction, and it comes down to the mechanism of synchronization. What is the actual computational difference between a work-stealing deck and a shared atomic counter?
I'm assuming the hardware overhead is vastly different.
Monumentally different. In Rayon's work-stealing system, threads are constantly pulling each other's memory spaces, utilizing compare-and-swap atomic locks to steal specific tasks from the bottom of a complex data structure.
Right, checking up on everyone.
It requires significant bookkeeping to know what has been stolen and what remains. What gnosis-frf implements with subchunking is a pattern called cooperative yielding.
Cooperative yielding.
There are no double-ended queues. There is no stealing from another thread's memory space. There is only a single shared integer sitting in memory and atomic counter.
How does drawing from the counter avoid the locking overhead?
It uses a specific hardware instruction called a relaxed atomic fetch add.
Relaxed atomic fetch add.
Let's say M is 64, meaning there are 64 chunks of work. The counter starts at 64. Thread 1 looks at the counter and executes the fetch add instruction. In a single, indivisible hardware step, the CPU reads the value 64, returns it to thread 1 as its assigned chunk index, and decrements the central counter to 63.
And the relaxed part of relaxed atomic fetch add is key, right? We talked earlier about a release store creating a memory fence to guarantee ordering.
Precisely. A relaxed atomic explicitly tells the compiler and the hardware, do not create a memory fence here.
So no wall.
No wall.
No.
I don't care about synchronizing the broader state of memory across the cores. I just need you to decrement this single integer without 2 threads getting the same number. Because there is no memory fence, the instruction executes with virtually 0 latency.
Thread 1 grabs chunk 64 and processes it. If chunk 64 is just empty blue sky, thread 1 finishes in a microsecond, loops back to the central counter, and executes another relaxed fetch add to grab chunk 63.
Exactly.
The fast chunks are processed rapidly, keeping the idle threads constantly fed with new work. If thread 8 grabs chunk 40, and chunk 40 contains that incredibly complex character model, thread 8 will be bogged down for a long time.
But while thread 8 is trapped processing the heavy character model, the other 7 threads do not sit idle at a barrier.
Oh, they just keep going to the counter.
They continuously loop back to the central counter, cooperatively yielding the remaining chunks of work among themselves. The slow chunk runs to completion on whichever worker drew it, but the overall throughput of the system remains high because the other cores are churning through the rest of the data.
It preserves the low overhead static architecture because there was no complex bookkeeping and no cross-thread memory stealing. It is just one integer that everyone agrees to decrement.
Yes.
Let's examine the benchmark data for this cooperative yielding model. They tested it on an incredibly skewed, unbalanced workload. The dataset contained 100,000 elements, but the last 10% of those elements took 100 times longer to process than the first 90%.
A workload where the difficulty is massively backloaded is the ultimate worst-case scenario for a static split. If you use a simple k-way split, the thread assigned to the final lane will receive almost all of the heavy computation, while the other threads finish immediately and idle.
The numbers reflect that perfectly. When they ran the pure static k-way split on this deeply unbalanced data, The median completion time was 50.17 milliseconds. It was bogged down by the slow lane,
But then they engaged the cooperative yielding mechanism with subchunks.
using 2048 chunks.
Right. This split the data into 2,048 chunks. The median time plummeted from 50.17 milliseconds down to 13.7 milliseconds.
That's a huge drop.
By breaking the work into smaller, cooperatively drawn pieces, they effectively distributed the dense 10% of the workload across all the threads, rather than trapping it in a single static lane.
But critical comparison is how this 13.7 millisecond time fares against Rayon.
Yes, Rayon is designed specifically to conquer unbalanced workloads.
Yet on this exact same unbalanced dataset, Rayon's median completion time was 14.49 milliseconds.
It's slower.
gnosis-frf's 13.70 milliseconds is faster than Rayon's 14.49. At this tuning sweet spot, where M, the number of chunks, is roughly 20 to 30 times larger than the number of threads, FRF actually beats Rayon on Rayon's own home turf, entirely without dick steals or per-item locks.
The mechanism of a single relaxed atomic counter per course chunk proves to be more hardware efficient than a complex work-stealing engine, even when chaos is introduced.
Are there any downsides to this subchunking?
Well, however, the documentation outlines a critical nuance regarding the size of the chunks. If you split the work into too many tiny chunks, you recreate the tax problem.
How so?
If the chunks are so small that they take only a nanosecond to process, the threads will spend all their time hammering the central atomic counter. Even a relaxed atomic operation becomes a bottleneck if 8 cores are trying to decrement it millions of times a second.
The overhead of checking the counter starts to outweigh the actual work.
To manage this, the with subchunks auto algorithm intelligently calculates the chunk size. It aims to keep the chunks large enough that the threads spend the vast majority of their time executing the mathematical workload.
But small enough that cooperative yielding can effectively balance any unexpected heavy elements.
Exactly. For extremely large datasets where the top-level chunks must be massive, they do document a fallback mechanism, a 2-level mini-batch stealing process. But the primary goal is to balance the scale of the chunks against the overhead of the synchronization to stay on the hyperfast single counter path.
So we've established how gnosis-frf handles current tangible chaos using cooperative yielding. But section 4 of this, README, the next frontiers, is where my understanding of computer science had to stretch.
It gets wild here.
We pivot from practical implemented scheduling into theoretical concepts borrowed directly from fluid dynamics and deep mathematics. They outline 3 frontiers that are documented but not yet implemented in the code base. The first one is the Reynolds adaptive spin window.
This represents perhaps the most ambitious philosophical leap in the entire architecture. They are proposing a self-regulating scheduler that doesn't just measure time, but measures the texture of the execution.
The texture. The text states they intend to track the EWMA, the exponentially weighted moving average, of the slowest versus the fastest timing ratio among the threads.
Right.
If that ratio exceeds the square root of 5, which is roughly 2.236, the workload is deemed turbulent, and the worker threads should park earlier. If the ratio is below that number, they should spin longer.
Yes.
What in the world do fluid dynamics, specifically Reynolds numbers and turbulent versus laminar flow, have to do with scheduling execution threads on a silicon CPU?
To bridge that gap, we have to examine what a Reynolds number actually represents in physics. In fluid mechanics, the Reynolds number is a dimensionless quantity used to predict fluid flow patterns.
Okay, stick with me.
It essentially measures the ratio of inertial forces, the momentum of the fluid pushing forward, to viscous forces, the friction of the fluid resisting movement. At low Reynolds numbers, viscous forces dominate. The flow is smooth, constant, and highly predictable. The fluid travels in parallel layers that don't mix. This is called laminar flow.
So like thick honey pouring slowly out of a jar.
Yes, or water flowing perfectly smoothly out of a tap.
Laminar is smooth, ordered, and highly predictable.
At high Reynolds numbers, inertial forces dominate. The flow becomes chaotic, unpredictable, and full of eddies and vortices. The parallel layers break down. This is turbulent flow.
Think of whitewater rapids crashing over rocks.
Exactly. The developers of gnosis-frf are drawing a direct, profound parallel between the physics of fluids and the physics of software execution.
The flow of data through the processor cores.
When the engine executes a parallel loop, it can measure the exact time it takes for the fastest thread to finish its chunk of work and the exact time it takes for the slowest thread to finish. By dividing the slow time by the fast time, you get a ratio. If you track this ratio over time using an exponentially weighted moving average, a statistical method that gives more importance to recent data points so the system responds quickly to changing conditions, you generate a continuous metric of the workload's chaos.
If the fastest thread takes 1.0 milliseconds to finish, and the slowest thread takes 1.1 milliseconds, the ratio is 1.1. The data is uniform. All the threads are operating in lockstep.
This is laminar flow. The execution is smooth and predictable.
But if the fastest thread takes 1 millisecond and the slowest thread takes 50 milliseconds because it hit a massive, complex block of data, the ratio spikes to 50.
The workload is highly unbalanced. The threads are completely out of sync. The execution environment is chaotic. It is turbulent flow.
The mathematical boundary they define between laminar predictability and turbulent chaos is the square root of 5. They call it the Hurwitz attractor, referencing something called the formalism under cam-diophantine armor.
It sounds like theoretical astrophysics.
It does. Where does the square root of 5 come from?
It originates in Diophantine approximation, a branch of number theory that studies how well real numbers can be approximated by rational numbers fractions.
Oh.
Certain irrational numbers are notoriously difficult to approximate. The golden ratio is the most irrational of all numbers in this sense, and its Diophantine properties are intimately connected to the square root of 5.
How does approximating fractions apply to the chaotic flow of CPU threads?
It connects through dynamical systems theory, specifically CAM theory, Kolmogorov-Arnold-Mosher theory.
Wow.
CAM theory studies systems that are subjected to small perturbations, like planetary orbits being slightly affected by the gravity of other planets. It asks the question, does the system remain stable and predictable, or does the tiny perturbation eventually cause the system to devolve into total chaos?
Oh, that makes sense.
CAM theory proves that stability depends on the ratios of the system's frequencies. If the ratios are sufficiently irrational, often bounded by constants related to the square root of 5, the system's invariant torics survive.
Oh.
It remains stable.
But if the boundary is crossed?
The system breaks down into chaotic resonance. The developers are postulating that in the microscopic ecosystem of thread execution, a timing ratio of approximately 2.236 represents the physical phase transition, where the flow of work moves from predictable, stable execution into chaotic, turbulent execution.
So if the scheduling system detects that the EWMA ratio has crossed above 2.236, it realizes it is no longer in a smooth stream. It is in a whitewater rapid of unpredictable data.
Exactly.
And because the data flow is turbulent, the arrival of the next piece of work is entirely unpredictable. Therefore, the threads shouldn't waste their 20 microsecond spin budget burning power while waiting, because who knows when the chaotic workload will allow the next dispatch to occur.
So the scheduler dynamically intervenes and tells the threads to park earlier, saving battery.
It acts as an intelligent mitigation for the pool cooling tail variance problem we discussed earlier. It senses the chaos and acts defensively.
Conversely, if the ratio is below 2.236, the system mathematically knows it is in smooth laminar flow. The data is predictable, the threads are finishing at the same time, the next piece of work is almost certainly coming right away.
So the scheduler tells the threads to expand their spin budget, staying awake longer to ensure they catch the immediate, predictable dispatch without paying the heavy unparked penalty.
It is staggering to think about a CPU thread scheduler self-regulating its sleep cycles based on Diophantine equations and fluid dynamics.
Truly. And they intend to apply this Reynolds adaptive logic to the subchunking as well. The second frontier is Reynolds adaptive M.
If the system detects that the execution flow has become turbulent, it dynamically increases M, the number of subchunks.
How high?
It might push the partition count toward incredibly high numbers, like k times 8122. By shattering the turbulent workload into thousands of microscopic pieces, it forces the system to cooperatively yield its way through the chaos, ensuring no single thread gets trapped by a massive block of work for too long.
But if the flow is laminar and predictable, it leaves M at a lower default level, avoiding the administrative overhead of millions of atomic counter decrements.
Right, and the third frontier is an adaptive steal threshold.
What's that?
Instead of using a fixed hard-coded rule for when to activate the mini-batch stealing fallback, it drives the decision dynamically from the observed computational cost of the chunks, not just how many elements are in them.
Oh, interesting.
High-cost, complex chunks can dynamically opt into the more robust stealing mechanism to ensure they are processed efficiently, while simple, cheap chunks stay on the zero bookkeeping atomic counterpath.
It envisions a parallel execution engine that acts almost like a biological organism, constantly sensing the texture, friction, and turbulence of its own environment and adapting its internal physics to match the reality of the workload.
While these are documented frontiers and not yet active code, they represent a profound shift in how we conceptualize software self-regulation.
Taking these mathematical and physical concepts and pushing them to their absolute logical extreme brings us to the deep end of the architecture, the section covering gnosis mapping and closed-loop metadata.
This dives into the philosophical topology that gives the library the gnosis in its name.
Yeah, it reads less like a software manual and more like an abstract mathematical proof.
They attempt to map the mechanical hardware-level orchestration primitives of the engine to a philosophical framework called the fork-race-fold triad from their formal ledger.
Let's walk through the triad mapping. First, they map the execute phase, the purely static k-way split where every thread gets a perfect lane, to the concept of fork.
Topologically, they define this state as truth, or SAT for satisfiability. It represents an invariant partition across k-workers. It is the foundational, undisputed truth of the system structure.
When the data is uniform, the static split is the perfect truth of execution. But as we discussed, the real world introduces unbalanced workloads. The system must adapt using with subchunks.
They map this cooperative yielding drain, where workers draw from the atomic counter to the race phase. And they philosophically define this as failure or departure.
It is a departure from the perfect static truth, because the initial assumption of uniformity failed.
The system had to abandon the rigid lanes and enter a state of dynamic adaptation to handle the chaos.
Finally, the per-worker partial reduce, the phase where the disparate threads finish their scattered chunks and combine their local results, is mapped to the fold phase.
They term this wisdom or gnosis. It is the integration of the parallel bearings. It is synthesizing the final, coherent answer from the chaotic, departed threads.
Here is the crucial topological claim they make based on this framework. Subchunking issues no topological debt because each subchunk is a fully formed boundary trace.
That's a huge claim.
I need to ground this intensely abstract terminology. What does topological debt actually mean for a software engineer who is just trying to make their physics simulation run faster without crashing?
Think of technical debt in software engineering. It is a shortcut you take now, a hack, a quick fix, that you know you will have to pay for later when the code becomes unmaintainable.
Right, everyone knows technical debt.
Topological debt applies that concept to the mathematical structure of the data processing. It implies that by breaking a massive, coherent workload into thousands of tiny, cooperatively yielded subchunks to handle turbulence, you have somehow damaged the structural integrity or predictability of the execution.
You have made the state of the system messy and difficult to verify.
You lose track of the boundaries, you don't know exactly what order the pieces will finish in, or if a piece got dropped during the chaos of the cooperative yield.
But gnosis-frf formally claims that because each subchunk is drawn cleanly from the atomic counter, processed entirely independently, and folded back into the final result through a mathematically commutative operation, there is zero debt.
A fully formed boundary trace means that every single operation is hermetically sealed.
The structural integrity of the mathematical operation remains absolute and verifiable, even though the physical execution was shattered into hundreds of unpredictable pieces across multiple CPU cores.
That guarantee of absolute structural integrity is what allows them to implement the most advanced feature in the documentation, the gamut braid closed-loop directive.
The documentation describes a metadata-only reader that is audited by something called node and emitted by a T-spridge. It introduces these functions called certified executional probes.
This is where we move from philosophical topology back into hardcore, verifiable execution logic. The gamut braid is not a mechanism to make the CPU run faster. It is a fail-closed certificate mirror.
What does a fail-closed certificate mirror actually do in practice?
Imagine you have a complex physics simulation loop that calculates the gravitational pull between a million asteroids.
Okay.
Running that full loop takes a significant amount of computation time. Now, mathematically, there might be a shortcut, a formula that allows you to calculate the exact aggregate center of mass without actually doing a million separate gravitational additions.
They call this a pressure-weighted representative reduction.
But as a programmer, you are terrified to use that shortcut in a production environment.
Why?
If the shortcut is wrong under some obscure edge case, maybe when two asteroids collide, your entire simulation breaks down, the math corrupts, and the application crashes.
You would rather the simulation be slow and correct than fast and potentially disastrously wrong.
The gamut braid provides mathematical correctness scaffolding. It allows the program to run both the full, slow, heavy workload and the fast mathematical shortcut side by side during benchmarking or runtime probes.
It then verifies them against each other using an equivalence probe.
The documentation lists incredibly specific trace metadata verifications that the engine looks for. Closed trace 10, 12, 17, 22, 43, 55, 10, axis 43, closure 55, total mass 1560, pressure weighted total 2586.
It isn't just checking if the final number is the same. It is cryptographically verifying the topological shape of the workload.
It is analyzing the exact structure of the data flowing through the parallel loops. It verifies that the mass, the pressure-weighted vectors, and the sequence of the workload precisely match a known, certified metadata certificate.
If the engine observes this exact data shape occurring at runtime, and it holds the digital certificate, proving that the mathematical shortcut yields an identical result to the full loop for this specific topology, it can safely and dynamically swap to the shortcut.
The performance data they show for these certified smoke runs is wild.
For a single-run certified workload, where the engine verified the topology and took the mathematical shortcut, the execution took 5.586 milliseconds. The fallback, where it didn't trust the shortcut and ran the full heavy loop, took 9.323 milliseconds.
The full loop was almost twice as slow. But the brilliance is that the engine isn't blindly guessing. It uses functions like certify closed loop weight accumulation to mathematically guarantee that the shortcut is valid before taking it.
If the metadata doesn't perfectly match, if the checksum fails, or if the data distribution looks even slightly different than the certificate, it fails closed.
It rejects the shortcut and reverts to the safe, slow path.
It automates the mathematical proof of correctness at runtime. It ensures that the transition from truth to failure to wisdom is mathematically unassailable.
It is a remarkable synthesis. It takes abstract mathematical theory, applies it to physical CPU architecture, and uses it to automatically optimize software execution safely.
Which really brings us to the synthesis of this entire journey. What started as a seemingly simple desire to run Rust code faster, to drop a 5-microsecond administrative tax, led us down an incredible rabbit hole of computer science and physics.
We started with the basic mechanical difference between Rayon's dynamic servers constantly looking for dirty plates and gnosis-frf's kitchen perfectly portioning out static meals.
We had to examine the physical reality of the CPU cache to understand why that mattered. We looked at 64-byte cache lines, making sure our independent threads weren't bumping elbows and triggering false sharing hardware invalidations.
We explored lock-free dispatch using unsafe cell and release store memory fences to bypass the operating system entirely.
We explored how a perfectly rigid static system adapts to unbalanced chaos through cooperative yielding, drawing chunks from a single relaxed atomic counter without falling back on expensive work-stealing locks.
We look toward the horizon, where the execution engine plans to use principles of fluid dynamics, exponentially weighted moving averages, and the Hurwitz attractor at the square root of 5 to mathematically determine if the data flow is laminar or turbulent, dynamically self-regulating its own spin cycles and chunk sizes.
Culminating in topological proofs for truth and wisdom, using closed-loop metadata to certify mathematical shortcuts at runtime without incurring topological debt. It is a breathtaking piece of engineering.
It really is.
For you, listening, the next time you open a high-performance application, take a moment to think about the invisible architecture running underneath it.
It is easy to take for granted. But every microsecond of latency you don't experience, every flawlessly smooth frame rate in a physics simulation, every instantaneous trade execution on a financial market, it is all the result of these microscopic, high-stakes battles over how to coordinate work across silicon cores.
It is a universe of complexity, constantly balancing chaos and order, happening millions of times a second.
Which leaves us with a final thought for you to ponder.
If we're reaching a point where our software's thread execution isn't just a list of rigid instructions, but is actively being designed to perfectly mirror the physical laws of fluid dynamics, using ancient Diophantine equations to separate turbulence from calm within a CPU, we still just writing code.
Or are we beginning to simulate the natural physics of the universe directly inside our processors?
The boundary between software and physical law is dissolving.
Until next time.